We'll start out today on optics in chapter 33 on models of light. This is wave optics, and pretty short section here. Chapter 33, wave optics. And with wave optics, that's a model of light. Again, these are models or simplified versions of reality. It's not what's really happening, it's our understanding of what's occurring, and we're putting our concept of how life works onto the universe, on how these models act. It works, it's predictive. All models break down, of course, at a certain point. We know that with the coronavirus models, not all models. Some models are better than others, and depending on how the outside parameters of our models, of course, work better at other times than not. But these models we're going to be talking about, in this case, the ray model and the wave model, and we'll give a little bit on the photon model, which kind of combines the two a little bit. Just going to talk a little bit about those, talk a little bit about what light is and what it isn't. I was going to put it over there, but it fell from last time. And just want to talk a little bit about intro to light. So optics, we talk about optics. Optics is the study of light. Directly out of your book. I've done a lot of work in optics myself, studied light a lot in my work. It's been a lot of fun. It's one of the reasons I went back to grad school was to study light more. Now, the first real text on optics was Newton. Isaac Newton, of course, wrote a book called Optiques. And basically Newton espoused what we're going to see, that light traveled in straight lines like a particle. Newton kind of wrote a book on it. He talks about different phenomena and stuff. Read here just for a second to make sure. He called them these particles, he called them corpuscles. I don't know why. But he called them corpuscles, these particles. And it's a bunch of like little particles going around in a straight line. We would now call this the ray model of light. And you can explain a lot of phenomenon with light using this ray model of light. Light goes in a straight line, reflection, refraction, the bending of light through a material. It can all be explained decently using the ray model. There's something called ray tracers in optics that trace the light rays going through things. They work on this model. They work pretty darn good. The problem is this didn't account for all the phenomenon that light had showed. Actually the guy named Thomas Huygens, but I won't get to him. Thomas Young. What he noticed was when light goes through an opening, it will spread apart. Basically, diffraction, which is what we're going to get into more. Now I'll do a few little demos. I got a red laser and a green laser. I'll do some demos. Diffraction occurs with light when going through narrow openings. You got narrow openings, light kind of acts a little funny. Light beam be straight out, gets spread apart. And sometimes there's gaps in that spreading apart of the light. What the heck causes that? Can't explain that using the ray model. So, how did he get to explain it? Well, he looked at some of the work that Huygens done some work with waves. And with waves, you can see that if you go take a wave through a small opening, like in a lock for, not Loch Thronberg. Come on. take a lock, and we're not going to spread lock around and put parts of it here and parts of it there and stuff. That would be mean. But what happens is when it goes through like canals and stuff, like Panama Canal, when it goes down, you can see light going through, should be water going through these openings, and it would spread out. And sometimes it would spread out, and these tops you'd have, and two on beside each other, sometimes you'd have places where you'd see a wave and not see a wave. And it matched some of the stuff Young saw with diffraction. This diffraction that occurs led people to what we call the wave model. Okay? Here that light acts as a wave. Now at the time they were thinking more compression wave. Of course with what Maxwell showed, it's more like a sine wave or a transverse wave. But that light has properties of waves. And this wave and particle duality, they call it, issue, happened for a while. Which one's which and stuff. But over time, especially with some of the modern work we did in the late 1800s, early 1900s, we started seeing some quantum stuff going on, and we developed what we now call the photon model, which really says light's not a machine gun spewing bullets. It's not a bunch of waves coming out like this. It's kind of in between. It comes out like this, and then it dies off. And this, you can call this a wave packet, or I bet you have an idea what this wave packet is called. It's called a photon. This photon here of light coming out. So it's a packet of energy that comes out. And what's interesting with this photon model is it says light is emitted and absorbed in discrete packets or photons of energy. Make sure that's what I want to say here. What do we know about these packets or photons? Has properties of waves and particles. Or as Newton would really want us to say, because Newton was fancy, corpuscles of these particles. And those are the three models. Now, which one's the most newest model? Photon model. Which one tends to explain things the best? Well, photon model. Which one's hardest to understand? The photon model. Which one's real simple to understand? The ray model. But it works in lots of situations. The wave model works in situations the ray model tends to have issues with. Now, the wave model can look like the wave model, the ray model, I should say, but to make the wave model here, show things a ray model shows easily, the mathematics can be horrendous a little bit. It's a lot of work. The photon model has even worse math, or better math, depending how you look at it, right, Cameron? But the math here, much more high level, but you can make predictions as rays and waves. Those are the three models. Of course, one scientists focus on the most now is the photon model when they're doing research. We're going to start out with waves and rays. For most of the work people do, though, these two models suffice. It's good enough for government work, right? Okay. And those are the three models. And interference is next.